So we're going to go through the emotions of seeing if it is exact, and then we're going to figure out if we can make it exact. So let's do that by starting right here with identifying our M&M. So once we identify what our M&N is, we can take the partial derivative of m with respect to y and set it equal to the partial derivative of n with respect to x. So the partial derivative would be 1 is equal to (2x minus 1). So the partial derivative of m is not equal to the partial derivative of n. But using formula number 3, we could see if we could find a function such that if we multiply the differential equation by, we can make it exact. So there's two different formulas we can use. One will get a function of x, and one will get a function of y. If we get a function with both both x and y in it, we're unable to make it exact, and we have to find a different method of solving the differential equation. So let's try formula number 1, which is the partial derivative of m with respect to y minus the partial derivative of n with respect to x divided by n. Now notice, this is how I remember it. The end function, what you're subtracting by, will be on the bottom, and what you're taking the derivative with respect to will be the function that you're hopefully trying to obtain. So given that these are partial derivatives, we could just plug it in, and the rest is just algebra. The question is, does it equal an f of x function? Meaning, is there only x's in this function? And it looks like we're missing a y right here. So that there's a y right here. And there's a y right here. Let's see. And there should be a y right here. So this is just an algebra thing that we're going to try to manipulate in order to have only an x function. There's a couple things that we could do. We're going to simplify the top part by saying 2 minus 2xy divided by, and we could pull out an x right here, and we're left with xy minus 1. And we could pull out a 2 on the top. And we're left with 1 minus xy over x times xy minus 1. Now I'm sure you could see that if we pull out a negative, if we switch the sign inside of these brackets, we'll obtain the bottom. So we'll just pull out a negative 1. And we're going to be left with xy minus 1 over xy minus 1. It turns out that there is an f of x function of negative 2 over x. Now, since we obtained an f of x function right here, then there is some function that we could find that if we multiply it by the differential equation up here, we will be able to make this differential equation exact. So using that formula, mu is equal to e to the integral of f of x dx, where f of x is negative 2 over x. This ends up being e to the negative 2 ln x, and it ends up being x to the negative 2 by bringing this property of logarithmic functions and these canceling, you obtain just x to the negative 2 as that function that we can multiply the differential equation by in order to make it exact. So let's do that. Let's take this equation and multiply it by x to the negative 2. So if we multiply this by x to the negative 2 and this by x to the negative 2, we'll get 3 plus y x to the minus 2 dx plus y minus x to the minus 1 dy is equal to 0. So let's use this first equation test by saying that this is m and this is n, and we take the partial derivative of m with respect to y, we'll obtain x to the minus 2 is equal to negative 1 x to the minus 2, and now it satisfies the test to see that now this new differential equation is exact. So we forced this non-exact differential equation to be exact, and now we could use the exact method in order to solve the differential equation. So using equation 2, we can say that the partial derivative of some function is equal to m, which is this part right here. So we could say that the partial derivative of some function with respect to x is equal to 3 plus y x to the minus 2. And if we take the integral with respect to x, and we add some constant that we lose, but that constant is a function because we're dealing with partial differential equations, that if we take a partial derivative of this function with respect to one variable, then the other variable that's within the function will be a constant and will lose some function g of y. So let's find out what that g of y is. So again, this dx cancels with this dx, and this integral cancels with this partial derivative operator, and we're just left with some function x, some function, capital F, of two variables, x and y, and it's equal to this integral and this constant function with respect to y. So when we take the integral, we're taking the integral with respect to x, so we're just going to tack on an x here. And then we have to treat y as a constant, so it's going to stay like that. And this x will be added once to the exponent, and whatever the exponent is will be in the denominator, added to some g of y function. So now we have 3x minus y x to the minus 1 plus some g of y function that we don't know is equal to some f of x function that has both x and y variables in it. So at this point, our whole goal, we found that function for the differential equation up here, but we don't know what function we lost when we took the partial derivative of this function with respect to x. So if we look up at this formula, we could say that the partial derivative of the function with respect to y is n, and we know what n is. N is this function. So what if we took the partial derivative of this function with respect to y, and then the partial derivative of this function on the right side with respect to y? Then we will find that we could set whatever we find taking the partial derivative to, we could set it equal to n. So that's what we're going to do. So we know that the partial derivative of f with respect to y is equal to, now we're taking a derivative with respect to y, so x is a constant, so that's 0. And over here we're taking the derivative with respect to y, so x to the minus 1 is constant, and the derivative of y is just 1. And a derivative of a function is just denoted like that because it's some general function. So now that we obtained the partial derivative of f, we could set that equal to n. So n is right here. So y minus x minus 1 is equal to, we forgot a negative right here. So y is equal to, y minus x to the negative 1 is equal to, which is our n, negative x to the minus 1 plus g prime of y. Now we notice that these will cancel, and our g prime of y function will be equal to just y. Now if we take the integral of both sides with respect to whatever variables inside of this function, we'll be able to obtain our g of y function that we lost when we took the partial derivative of capital F with respect to x. So this is y squared over 2. Okay. So now that we found g of y, we can finally plug that in to this function that we obtained earlier, which is the f of xy function that is the solution to the differential equation that we're solving. So this means that f of x and y is equal to 3x minus y x to the minus 1 plus this g of y function, which we found that it was y squared over 2. And this is the solution to our differential equation that we started with. Again, we could check our solution by taking the derivative, not the partial derivative, the derivative of this f of y function, and see if we can obtain the original differential equation that we started off with. So taking the derivative, we have d of f over d of x is equal to d of x is equal to 3 minus y is a constant, so we're going to keep that there, and we're going to drop down this negative 1, which makes this a positive. This ends up being x to the negative 2. Then we're going to add, and we're going to drop down the 2, which will cancel with the 2 on the denominator, and we're just going to be left with 2, but the 2 cancels, and we're just going to be left with y. Actually, we're not taking partial derivatives here, so let's go back and rewind and notice that this is a product rule with implicit differentiation, because we're taking a derivative with respect to x of a variable that is not x, which is y. So we're going to use f prime g plus g prime f, and the derivative of negative y is just negative 1, and we're going to copy down x to the negative 1, and we're going to add that to the derivative of x to the negative 1, which is going to be a negative x to the minus 2, and we're going to copy down negative y, which makes it positive y, plus y and when we take the implicit differentiation of y, we need to tack on a dy dx. So this will be minus 1 dy over dx, and then we copy down x to the negative 1, and then we should have a dy over dx right here. So now we're going to so this function f of x should equal some constant, but we don't know what that constant is. So this function, because it's equal to a constant and we took the derivative of it, we could say that it's equal to 0. So our dy over dx times -3 x to the -1 plus our y dy over dx, and we're going to bring all of our constants back. So this -3 is not right there. This is just negative. And so we're going to subtract 3, and we're going to subtract x to the -2y. And we're going to be left with a -3 plus x to the -2. So when we factor out a dy over dx, we're going to be left with y minus x to the -1 dy, and then we're going to multiply both sides by dx, and we're going to be left with this. Now adding 3 plus x minus 2 dx on both sides, we'll get 3 plus x minus 2. And this has a y right here. So it's very easy to make mistakes here. So this has a y right here. dx plus y minus x minus 1 dy is equal to 0. Now remember what we multiplied this function by? We multiplied it by x to the -2. So we're going to remove that x to the -2 by doing the opposite, by multiplying x squared on both sides. So this will make 3x plus y dx plus x squared y minus x dy is equal to 0. And hopefully, if we did everything correctly, this should be the original function that we started off with. And let's see if it is. So it looks like we're missing an x squared, so we might have made a mistake when we were testing our solution. And it looks like we did. So notice when we factor in this x to the minus x squared, this isn't just x, this is x squared. So it looks like we did everything correctly, except for this x squared right here. And if we look at what we started with, it looks identical to everything else. So we have confirmed that this is the solution to the differential equation.